In a previous video, we talked about what happened when we rolled off a cliff or a table heading flat, and we also talked about what happened when we launched at an angle on a flat ground. Today we're going to put those two ideas together, because very rarely are you going to launch from flat ground to flat ground, or are you going to roll off the cliff perfectly flat, because very few things in the world are perfectly flat. And from a certain point of view, it's more advantageous to shoot or throw or whatever from a higher elevation. Cannons, for instance, the higher up they are, the farther they'll go because they have that extra elevation to help them out. If you're taller, it's easier for you to get further throws with a football or basketball. Either way, height pays off. So what we're going to start looking at is how that height influences and impacts the travel of projectiles, starting here. Now, we've already talked about this problem. We have a cannon, for instance. It's firing a shot at 115 meters per second at a 40-degree angle. How far does it go? Well, if it's on flat ground, we can just use the range formula. Plug in our initial velocity, plug in our theta, plug in 9.8 for g, and we'll get an answer. (1328.99 meters). Done. Easy. The reason we can't do that up here is because that only goes to the same height. That formula only works if you're returning to the same y value. So if we wanted to know how far it goes to this point, absolutely, but there's still this drop off we haven't accounted for. So what we need to do is we need to factor in the height of the cliff when we do our calculations. In this case, this cliff is 90 meters tall. Well, how does this look? How does this work out? Well, just like previously, we'll have x and y variables. So let's just do that now. X, y. For the x direction, we're looking for how far it goes. We know that our v initial x will equal our v final x, which will equal something. We'll be able to split this up and get that. We know that our acceleration in the x direction will be 0, but we don't know the time currently. We'll have to get that from over here. Over here, delta y is negative 90 meters. Why is it negative? Two ways. Number one, if we say the ground is 0, I went from 90 to 0. 0 minus 90, negative 90. Alternatively, if we say this is 0, and this is down, you have to go down negative 90 meters to reach the ground. Either way gives you your answer. Y equals negative 90. V initial y, we'll have to get from the cannon. The final y, we will also have to get somewhere else. Acceleration in the y direction, however, is negative 9.8. It's always 9.8. We're saying down is negative, so negative 9.8. Again, we don't know t. This change here guarantees we will end up having to do the quadratic. And while a lot of people hate the quadratic, you're going to have to get very familiar with it. Again, once we're in person, I can show you some tricks on the calculator to make it easier on you, but get the practice in now. So solving will be exactly the same. Split this up into x and y components, that 115, and x and y components. Solve for t here, plug in here. Go ahead, do that on your own, check back after. So I followed through on the math. I started by breaking up my 115 into components, and then I followed through, carried out, got my 2 times, ignored the negative time because it doesn't make sense, used the positive time of 16.22 seconds, carried that up here, and carried through the math. I got 1428.75. Now, an important note here. I did not use any rounded numbers till the very end. I used 88.10, the full thing in my calculator. I used the full time. I reported rounded answers for bookkeeping, but when I plugged in the numbers to solve for this, I used the numbers in my calculator. Had you used the rounded numbers, you'd get 1428.98, which is, again, a small deviation, but over a long enough scale, it'll add up. So make sure you're using best practices and not rounding your numbers till the very end. This is the number you should get for your range. Everything should be awesome and amazing. And you'll notice by going up 90 meters, we add 100 meters to our range. We go 100 meters further, minus a few centimeters, and there we have it. So having height is an advantage. Now, maybe not as much for football, where you only are about a meter off the ground, but it does help. It does add up. So another problem up here for you all to try, make sure you understand what's going on. A common question we run into physics is, will it make it? Not how far does it go, but will it make it? So consider, you're sitting in class or your room, and your friend bets you can't make the basket from where you're sitting. Distance 5 meters, which is about 15 feet. So it's a fair thing to say, or question, if you can make it with a little paper ball. Now, when we ask this question, what we assume is that this distance here is false. We only use it as a litmus check. We go through the rest of the problem normally. Okay, the ball is being thrown at 7.1 meters per second, at a degree of 25 degrees above the horizontal. You're throwing from a height of 1.2 meters above the ground because you listen to my lectures and understand that the height gives you a little extra distance. Does it make it? Go through this problem on your own. Solve it out. Solve for how far it will go, not using the 5 meters. And then once you figure out how far it goes at the 25-degree angle, if it is more than the 5 meters, at the 5 meters, or less than the 5 meters, will tell you whether or not you can make it. I will say right now, as plenty of people will tell you, that there's a backboard in the form of the wall, often behind this, that it can bounce off of. And if you can overshoot it, you can short sell yourself to make it in. But do go ahead, do the math, see how it pans out. Okay, let's take this one from the top. First thing I did was I break the velocity into components over here in blue. I got a velocity for the y of 3.0 and a velocity in the x of 6.43. Once I had those, I plugged them into my givens. Using that, I solved for t using my y values, or once I solved for t and my y values using the quadratic here. We had two answers. The 0.28 negative doesn't make any sense, throw that out. Leaving me with 0.89. I take that over to my x, because they're at the same time, solve it through, and I get 5.71 meters, which means you can throw it 5.71 meters at that angle. You'll probably hit the backboard and then into the basket, or you'll have to shortchange it a little bit. But you can make that throw. And there you have it. If you would like to see a challenge problem, see the upper limit of what this problem might look like or the test might look like, go ahead and keep watching. Otherwise, you're done for today. Okay, here's a really challenging one for you. In parkour, it's very common for someone to leap off one building and land on another that is a lower height. This is very impressive looking. It shows up in movies. It's a common thing in parkour videos. So in this case, a person is running along this rooftop. They want to leap and land on this rooftop. The distance between them is about 7 meters, which is, for reference, about 20 feet. The question I want to ask is, how fast does the person need to be traveling to make this leap? The person's going to leap between these two. And they're going to leap at a 30-degree angle. I'm not telling you how fast they launch. We're just going to make this a little hard. It makes it the challenge. Now, some hints. First and foremost, you're going to have to work backwards. You're going to have to figure out exactly how long they're in the air for and the velocity. You'll end up with a system of equations. You'll have two equations, two unknowns, and you'll need to plug one into the other to solve it. Number two, the 12 meters here and the 7 meters here aren't exactly useful directly. You'll need to use them, but the only thing you care about is your change in y, not the y value. Number 3, if you're going to solve this symbolically, it will get messy. If you're solving it numerically, it will get messy, but less so. Please make sure you're using your sines and cosines. Check all of those. I'll post a symbolic answer elsewhere, but I will be solving this one numerically just to help everyone out. Go ahead and give it a try. I started by plugging in all my givens, all my unknowns, and I set the two equations up. X equals v naught x times t plus 1/2 ax t squared. I plugged in v naught cosine theta for my v naught x. I plugged in 0 for a, gives me this equation here with all my plugged in variables. I did the same for y, and ended up here. Now I have two equations with two unknowns, v naught and t. What I did then is I rearranged this equation to solve for t. And in doing so, I could simplify it down to here. Once I had this, any place I saw t over here, I could plug in. And that's what I did. Instead of v naught t, I had 0.05 v naught 8.083 divided by v naught. And the same thing here. When I follow through the math, this simplifies to 4.04 because the v naughts cancel out. I square the number on top, I square the v naught on the bottom, continue on with the algebra, and end here, giving you 5.95 meters per second. If you want to see this symbolically, there'll be another video about that. Heads up, that one looks really ugly. But there you have it. That's how the challenge kind of works. If you can solve this, if you can do this, this makes sense to you, there's nothing I can do in projectiles that will scare you or surprise you. This doesn't make sense. You have a little bit to go. Don't worry.